this computer. And we'll share the screen. Okay, so again, we're working on the handouts. So the week 5 handout, and again, question 1 and question 2 are pretty straightforward. You just have to actually do them. And again, the real question is how many people are actually paying attention to this section with a quiz tomorrow. All right, so question 1. Oh man, my pen just died. So we're given this long element of S10 in cycle notation. Note, though, that this is not a disjoint cycle, right? These are not disjoint cycles. So we can't immediately just conclude the inverse and the order of alpha from this. What we have to do first is compute its cycle decomposition. So why don't you start that? I'll give you a couple minutes. But once you compute the cycle decomposition, finding the inverse and the order are very straightforward, right? So question 1 is really about finding the disjoint cycle decomposition. So we have alpha. Let me just write it down, and then we'll take a little break to see if we can't answer it. 5, 4, 3, 9, like that. 1, 3, 7. 8, 5, 4, 2. Okay, and remember, when you're doing this computation in this class, because different classes are different, actually, there are actually 2 ways you can read it. We read this as being composition, function composition. So we read it from right to left. Okay, because if you read it from left to right, you'll actually get a different answer, right? So make sure that you're reading it from right to left. And then I might actually show you a slick little trick to double checking your answers if you want more practice. Okay, so let's spend 4 minutes or so on that and see where we get to. Okay, so hopefully that was long enough. Sometimes you have to, there's a lot of tracing that you have to do. So definitely, maybe I stopped early. And if you did, you can yell at me and say, no, I need more time. It's hard to show the work for this because basically you just have to start at like a number and trace it through. So maybe I'll do like one number and see if we can figure it out. So, I usually start at 1. That's a very reasonable place to start at. And we're going to read right to left, right? So we're going to figure out where 1 maps to. So here we get that 1 maps to 3, right? Then I look at the next cycle. What does 3 map to? 3 maps to 2. In the next cycle, there's no 2, so 2 is fixed. 2 maps to 2. And then in the final cycle, 2 maps to 4. Right? So I would get that 1 in total, after tracing everything back, 1 maps to 4. Now at this point, I would do the same sort of thing. I would start at 4 and trace it back. And the reason why I'm not going to start at 2 is because I'm trying to complete this cycle, right? So the next number here is 4. I'm going to start on the right-hand side, figure out what 4 maps to. 4 maps to 2, 2 maps to 8, so on and so forth, right? And when you get this, you should compute 1483795. Okay, so did anyone else get that? Hopefully I'm not crazy. Right? And I mean, I say, did anyone else get that? But I know that's the right answer. So, because I checked with a computer. But let's suppose I didn't know that. I'll show you how to check it with a computer in a second. From this immediately though, we get the order of alpha, right? So from this, oh man, this pen is just dying like crazy. I might need a new battery here. Hopefully I can get through this without needing to pull out a battery. But what's the order? What's the order of alpha? Based off of what we learned last time. 12, exactly, right? It's the least common multiple of the cycle lengths. So in this case, 3 and 4. So from this, the order of alpha is the least common multiple of its cycle lengths, which gives us 12. Right? And what's the inverse? Or if you don't want to write it down, you can just tell me what I'm supposed to do. Give me the algorithm for computing the inverse. Yeah, beautiful. 841 5973. Okay. And the reason is we talked about this last time. If I give you a cycle, the inverse of that cycle is just to write it backwards, right? And then you might say, well, okay, but we didn't talk about what to do with 2 different cycles. How do I know that this will work? Well, remember, disjoint cycles commute, right? And so because these 2 cycles are disjoint, if I write each of their inverses, right, basically here, let me show you. So if we write alpha times alpha inverse, that would give me 1483795. Then I'd multiply it by the inverse, 841. 5973. But if you look at this cycle, it is disjoint from this cycle, right? Which means that I can actually switch the 2 of them. And then once I have the 148 and the 841 together, they'll cancel out, right? So 148, 841, those 2 will cancel each other out. And then these 2 will also cancel each other out. And that will give you the identity permutation, right? So if you're given disjoint cycles, it really is just as easy as writing them backwards. If they're not disjoint, it's not that straightforward, because in your head, you still want to be like, okay, if I write it backwards, it should still invert. But the thing you have to be careful about is making sure that the cycles commute. So basically, if I give you something like alpha above here, which is not disjoint cycles, you can still compute its inverse by writing the cycles backwards, but you also have to reverse the order of the cycles, right? Just like when you write a matrix AB inverse, it's B inverse A inverse. You actually have to switch the order of the multiplication. You can do the same thing with alpha here without it being disjoint by inverting each cycle separately, but then you also have to invert the order in which they appear so that when you write them beside each other, you get this kind of like, collapsing center. So just make sure that you do that if you want to use the original cycle definition of alpha in order to do it instead of computing the disjoint cycles. Okay. So I think that takes care of question 1. Now for question 2 can just be answered immediately. And I wonder if anyone can tell me how to do it. So we've got beta. I'm not even sure I'm going to give you time to do this. 1, 3, 5, 7, 9, 8, 6, 2, 4, 10 in S10, right? What is the smallest n such that beta to the n is beta to the -5? Okay. There's very little to do here. What do we do? Let's just think about it together. See if we can come up with it. Anyone have any ideas? The order of b minus 5. Yes, absolutely. I agree. It's the order of b minus 5. And the reason for that, right? Exactly. So if we take, let's multiply both sides by beta to the 5. No, I think I'm going to need a new battery here. Just give me a second. Stupid thing. Why you got to die on me in the middle of a lecture? Seriously, you got to replace the battery like once every couple of years. And of course, this is when it happens, right? And if I can't replace the battery, if replacing the battery does not fix the pen, then we're in trouble. Did I put that in backwards? Okay, so, do this ahead of me, anticipate what I'm going to do. So I'm going to multiply both sides by beta to the power of 5, which will give me the identity on the left, right? So to multiply by beta to the 5 to get beta to the n plus 5 is equal to the identity, right? So n, whatever n is, we want the least number n such that beta to the n plus 5 is equal to the identity. N in this case should be, right? Like basically we need this thing to be n plus 5 to be the order of b. Right? Because that's the definition of the order of beta. It is the smallest exponent such that beta to that number is equal to the identity. If we want the smallest positive natural number n such that this is true, well, then that exponent has to be equal to the order of b. So or n is the order of beta minus 5. Okay, so what's the order of beta? Exactly. Or we could just skip that Hongwei, like you're absolutely correct, but let me just cheat and just say it's equal to 21, right? But you're absolutely correct. The reason why it's 21 is because these are disjoint cycles, right? The first cycle, like if you check, it takes you a second to check, but there's no overlap between these two cycles. One has length 7, one has length 3. So as Hongwei says, their least common multiple is 21, and that tells us that the order of n is, or the order of beta is 21, right? So we know that the order of beta Or I guess I've basically written what you've written down, Hong Wei, but I'll just write it slightly differently, but you're 100% correct. So n is 21 minus 5, or 16. Right. That one's not too bad, I think, especially since it was given to you as a disjoint cycle to begin with. All right, very good, very good. The next question, you know what I didn't do? Sorry, I meant to show you how you would actually compute like the cheating way of computing. Not that this is actually an academic offense, but let me show you this. Okay, so you can go to Wolfram Alpha. This is kind of going back to the first question. So if I go to Wolfram Alpha, you'll notice that this is exactly the cycle that we were given, although I've written it backwards. And the reason that I've written it backwards compared to what it was given to us is precisely explained right here, right? Wolfram Alpha says the product sigma tau represents the permutation tau sigma. So what that means is that Wolfram Alpha is doing it the opposite as we are, right? We read right to left, but Wolfram Alpha is going to read left to right, right? We interpret tau times sigma as being the composition directly, whereas it interprets them as being flipped. Okay, and if you go into here and you just say permutation, put in your permutation, but put it in reverse, it gives you what the answer should be, right? 1483795, right there, right? And you should be able to ask for like the inverse of this and all that sort of stuff. So that's pretty cool, right? And this means that if you want any sort of like practice on this sort of stuff, then you can just make up a cycle, basically write it down at random, try computing it, and then throw it into Wolfram Alpha and see if you got the right answers there. I don't think you'll probably need to spend too much time doing this sort of thing, but you do have a way of checking your answers, right? By plugging stuff into Wolfram Alpha. So if you want to check that out, that's kind of a nice way of verifying your answers, right? It's cool. Yeah, there's also another thing you can do. Yeah, or does it show the order? Oh yeah, so it does, look at that. Right? So, and yeah, actually, I don't know. Oh, it shows the longest sequence. Here's a cool thing. I like this like little map here. I think that's kind of cool, right? It kind of shows you how it actually works. All sorts of cool stuff down here, right? So yeah, you can plug that in. The other thing that you can do as well is to remember that permutations can also be written as matrices. And then if you're familiar at all with Octave or MATLAB, then you can do all of these things in terms of Octave and MATLAB. And in fact, you can write some functions which will do these computations for you. Or you can just write permutations as functions, as computer science-based functions, and then have, write some quick little code to, grind these things out for you. So lots of cool things that you can do in terms of actually computing this group stuff on a computer. And if you really want to get into this and get hairy, there's something called GAP, which is Group Algebra Program or something like this. And it's software designed entirely to compute all sorts of group theoretic properties. It gets a little bit hairy because it's actually designed for like research level group, exploration. But if you want to, it can do anything that you might ever want it to do, right? So you can check that out. It's a cool little thing. Okay, let me reshare this. All right, what's question 3 here? Let me see what this question is. The center. Oh, this one requires a little bit of work. Okay, so I'm gonna have to give you some time to do this for sure. So show that the center, right? That's what they're saying. The center of the symmetric group is trivial for n greater than or equal to 3. I think there's a second part, which is, also find ZS2. That part's boring. What is ZS2? In fact, somebody tell me, what is S2? Like as a group that we kind of know better, what is S2? Anyone know? Like if you just had to write it down, you could probably tell me what S2 is in terms of cycle notation. Yeah, right. So it's the identity permutation, and then the transposition 1, 2. Exactly. What's the order of, and 1, 2 squared is equal to the identity. So what group is this? Like what other way more familiar group does this look like? Anyone? Let me ask you the following. Is this cyclic? Is this group cyclic? Yeah, absolutely is, right? It's generated by the element 1, 2. So we're familiar with the cyclic group of order 2. This is basically Z2, right? I'm going to put the equal sign here in brackets, but this is basically Z2. And therefore, the center of Z2, well, Z2 is abelian, right? So the center of Z2 is everything. Right? That one's not too bad. Okay, so now it says, all right, if you, the moment you have any freedom whatsoever, and you're not just kind of the silly group, then in fact, the center of your group is trivial. So let me give you a little bit of time to play with that. I mean, you either, I feel like I should give you a hint. I would assume for the sake of a contradiction, here's my hint. So for the sake of contradiction, so for the sake of contradiction, assume you can find something in the center that's not the identity, right? So it's not the trivial permutation. In particular, it does, whatever, it's not the identity permutation, right? It flips at least two things around. Find an element which doesn't commute with it. Such that sigma tau does not equal tau sigma. Okay, so I think you could spend a long time thinking about this, and no amount of time that I give you would be enough if you're not thinking about it the right way. But I think that with this hint, this might be doable in 5 or 6 minutes, right? So assume that you have a non-identity element that's in the center, and then show that you can find an element which does not commute with it. And that's a contradiction because you assumed it commuted with everything, right? And you will very much see where the condition n bigger than or equal to 3 has to appear if you do it this way. Okay, so let's spend like 6 minutes or so. Let's see if we can grind out a solution to that. Okay, so does anyone think they managed to get this? I mean, it's hard to obviously write down an answer because it's a proof, but my question is, did anyone manage to arrive at something that they think was reasonable? All right, like I'm hoping so. Maybe. All right, let's take a look and see what we can do here. And let me try and run you through my reasoning here too as well. Again, we're just trying to arrive at a contradiction, right? So I just need to show that sigma tau is not equal to tau sigma. And to do that, I don't even need to show that they're not equal in their entirety. I just need to show that as a permutation, as a bijection on the set from 1 to n, that they map, sigma tau maps an element to one thing, and then tau sigma maps that same element to something different, right? And that would show that they're not equal. Okay, so in my mind, the proof goes like this. So since sigma is not trivial, it must map, it can't map m to m for every m, right? So since is not the identity, there must be some K and L such that sigma of K equals L, but K does not equal L. Does that make sense? Because if sigma of K is equal to K for all numbers 1 through n, so sigma of 1 is 1, sigma of 2 is 2, sigma of 3 is 3, so on, then that's the identity permutation, right? So in particular, there must be some set K and L such that sigma of K maps to L, but K and L are not equal, right? That's how you know you're not the identity. Okay. And so now what I basically want to do, here's what I want to do in my head. Let me show you. So pick some element P that is not K or L. And why can I do this? This is critical. Why can I find an element in the set 1 through n that is not K or L? Like what assumption did I make in the beginning of the question that allows me to do this? And notably, why does this not work in the case of S2? Exactly, because n is greater than or equal to 3, right? Right, which we can do since n is bigger than or equal to 3. And so we see that this proof would not work if we were doing it for S2, precisely because, well, K and L are the only two elements in the set. And once I kind of remove them, there's no way I can pick P. So now we see that the n greater than or equal to 3 condition is absolutely necessary, right? Okay, now here's kind of what's going on in my brain. So, obviously sigma is a function from the set on n elements to set on n elements. Now I don't care about what it does to anything other than K, L, and P, okay? So here's what I'm thinking. I've got K, L, and P over here. And I know sigma maps K to L, right? Now what I want to do is I want to find a tau such that this happens, okay? And only that happens. And then that way, if I flip them, right? Like in particular, I want K to map to K under tau so that this happens when I flip them, right? And you see now, do you see that like sigma and tau sigma will be different because when I plug K into both of those permutations, in the one on the left, K will map to P, but in the one on the right, K will map to L, right? And we've said L is not equal to P, and therefore we've arrived at our contradiction. Does that make sense? Okay, so what we need to do then is come up with a permutation tau, which should definitely be doable, that maps L to P, but does not do anything to K. And what what should I choose to do that? Like, what's the easiest thing that would do that? Yeah, exactly, just LP. Right? So it's just the transposition LP. This certainly doesn't do anything to K, right? It just leaves K alone. And then again, if we actually track what we get, so if we do sigma tau of K, well, tau of K is just K, so that becomes sigma of K. And sigma of K was equal to L, right? And then tau sigma of K is tau of L, which is equal to P. So sigma tau does not equal tau sigma. And we're done, a contradiction. All right, but this contradicts the fact that sigma was in the center, right? Because being in the center means that you commute with everything. And the assumption that we made was that there was some non-trivial element, non-identity element in the center. And so voila, we're done, right? We've proven that the center is trivial. Okay, so any questions about that? Does that make sense? Maybe let me zoom out here. Right, and that's just how I kind of like reason through it myself. Okay, I will assume that we're all right. Now, question 4 has a lot of parts to it. I want to just, knock out A really, really quickly. And in fact, I mentioned the answer to A at the end of the other day when I was talking about why aren't the odd permutations a subgroup, right? So we have HN, which is the collection of all. What you're going to do is you're just going to go through the symmetric group and you're just going to square every element. And once you square it, you throw it into HN, right? And so A is that show that HN is a subgroup of AN for all N. Why can I just immediately conclude this? Like there's no need to do anything. Right? And again, think back the other day into our conversation about why the odd permutations are not a subgroup. What happens when you multiply two odd permutations? Exactly. Odd by odd is even, right? So basically, even plus, so when you square or when you multiply two permutations, the number of transpositions that you require to write them out is going to add together, right? So in particular, if you square an element, if the original element was even, then the number of transpositions you need to write it down is even plus even, and that's an even number. If the original number was odd, then it's odd plus odd, but that's also even, right? So you can write it down more formally, but basically, even plus even is even. So if we started with an element of AN, it will be an HN. Odd plus odd is also even. So if we started with an element that had an odd number of transpositions, well, after we've squared it, we have an even number. So no matter what, alpha squared always has an even number of transpositions in it, which means it's an element of AN, right? Okay. Now B here, B is a little bit tougher. And I want to run you through it. Let's do this one as a class, okay? So instead of giving you any time, because we've only got 8 minutes left, I want to run through this together as a class, but I'm going to need your help, okay? So in every situation, I'm going to set it up, and I want you to knock them down, okay? And tell me what the answer is. And for this, it will have really helped if you've taken Math 202. So let's show that HN is equal, let's show that H5 is equal to A5. Okay, how many elements are in A5? Close. So 5 factorial would be S5, right? But A5 is only the even permutations. So we get exactly 5 factorial divided by 2, which is, anyone know? $60, right? So if we know that H5 is a subset of A5, if we can show that H5 has 60 elements in it, they must be equal. Do you agree? So we want to show that H5 also has 60 elements, because if, right, H is a subset of A has 60 elements, H has 60 elements, they have to be equal. Okay. So let's start seeing what happens when we square elements of S5. Now, we can write every element of S5 as a disjoint product of cycles, right? So what we want to do is think about all the ways that you can write something as a disjoint product of cycles. So what are basically the permutation? What are the partitions of 5? So we have, okay, somebody double check me here. Oh, you know what? Let me start at 5. So we have 5, 4 plus 1, 3 plus 2, 3 plus 1 plus 1, 2 plus 2 plus 1, 2 plus 1 plus 1 plus, those are just pluses now. And then 1 plus 1 plus 1. Do you agree? This is all the way that I can write 5 as a sum of of positive numbers. Did I miss any? I think I got them all, right? Okay. So these are, you might say, like, why did you write these out? Because these are the classes of elements of S5, right? We've got 5 cycles. We've got 4 cycles. We've got 3 2 cycles, right? So this, when I say this, I'm talking about stuff that looks like that, right? So it's a 3 cycle and a 2 cycle, but they have to be disjoint. Here we've got 3 cycles. Here we've got 2 2 cycles. Here we've just got straight 2 cycles. And then here's the identity. So does everyone agree that every element of S5, once you take it and write it as a disjoint product of cycles, it has to be one of these 7 things, right? It doesn't have any other options. It's got to be one of these things once you write it as a disjoint product of cycles. Okay. So let's figure out what each of these things becomes when we square it. And I think case 1, the easiest case, which things become the identity when I square them? The 2 cycles, okay, so 2 cycles. What else? There's other ones though. So certainly the identity, right? And exactly, Chief Arm, the 2 2 cycles also become the identity. Does everyone agree? So the identity of the 2 cycles and the 2 2 cycles all square to the identity. Okay, so they only add one thing, right? They all become the identity. So there's one thing. Group all produces just one element in HN. Okay, so this one, so this is done, and this is done. Okay, let's do 3 cycles. So 3 cycles look like A1, A2, A3. And if I square this, what do I get? Exactly, sure. Yeah, let me write that a slightly different way. Yeah, A1, yeah, it's A1, A3, A2, right? A1, A3, A2, which I think is actually a little bit different than yours, Qifeng. Yours, A2, A3, A1 is actually A1, A2, A3, right? They're the same. It doesn't just move them down. A1 is going to jump over A2 and then map to A3, which then jumps over A1 and maps to A2, right? Okay. So what we notice is that 3 cycles are preserved under the squaring map, right? 3 cycles map to 3 cycles, and in fact, do so bijectively, right? Certainly, it's, I mean, you'll have to maybe think about this a little bit to convince yourself, but there is a bijective correspondence between 3 cycles and their squares, right? So every single 3 cycle is the square of another 3 cycle, and the only way 2 cycles square to be the same thing is if they started as being the same 3 cycle. So there is a bijective correspondence here. So the question is, how many 3 cycles are there? Does anyone know? No? What is this? 5 factorial. Well, let's just write it out. 5 factorial divided by 2 factorial times 3. So that's 120 divided by 6. So that's 20. Right? 5 pick 3, because you've got 5 numbers to choose from in S5. You're going to pick 3 of them. The order of them matters. But once you've picked them, cyclic, writing 1, 2, 3, 2, 3, 1, and 3, 1, 2 are all the same. So we're going to divide by 3 to get the total number, right? So there's 20 of them. All right, let me go a little bit faster because I think we're running out of time. So that takes care of that. The 3 2 cycles are the same as the 3 cycles. Let's say the 2 3 cycles just produce the 3 cycles, right? Because when you square it, the 2 part becomes the identity. And so the only thing that matters is the 3 cycle portion, but you just generate all the elements that we did in case 2. So nothing new happens. The 4 cycles, so the 4 cycles, when we square them, become something interesting. These become A1, A3, and A2, A4, right? And they bijectively map onto this set. In fact, they surject onto the set, but they biject onto the set as well. So how many 2 2 cycles are there? Anyone know? Okay, so that gives us 15 2 2 cycles. And then what's our last case? Oh, it's just the 5 cycles. And so if we take A1, A2, A3, A4, A5, and we square it, we get A1, A3, A5, A2, A4. So the 5 cycles bijectively map to each other. How many 5 cycles are there? So there's 5 factorial divided by 5. So that's 4 factorial equals 24 5 cycles. And so if you add them all up, what do we got? We got 24. So the order of H5 is 24 plus 15 plus 20 plus 1, and that's 60. And so we're done. Right? And that's how you do this problem. So this was, I'm sorry, I'm a little bit over. So that's how you do H5. That's the hardest one. Go and do H4 and H3. The counting arguments are much simpler. But do H4 and H3 and convince yourself of the same sort of thing to see that they're actually equal. And then for H6, when you want to show that they're not equal, just explicitly construct an element of A6 that's not in H6. Okay? So any questions about that? Why is it 5, choose 3? Okay, yeah, sure. So for the 2-2 cycles, you want to know how many ways are there of doing this? A1, well, let me just write it as A1, A2, A3, A4. Okay, so there are 5 choose 2 ways of doing this. Oh, wait, did I write 5 choose 3? Oh, sorry, it should be 5 choose 2. You're right. Sorry, that's me just being dumb, right? Does that clarify it? Did I just miss? Yeah, okay, perfect. Yeah, it's 5 choose 2, right? The order certainly doesn't matter because it's a transposition. You've got 5 numbers, you want to choose 2 of them. Yeah, yes, and they are the same way. Because 5 choose 3 is me choosing which 3 numbers I don't want to put into that first cycle, right? Yeah. And then I divide by 2 because once you have the 2 disjoint cycles, this cycle is the same as this cycle, right? So I have to divide by 2 as well. Just for anyone who's wondering where that division by 2 comes from, this cycle is the same as this cycle because they're disjoint. So I have to divide by 2 just to make sure I've counted them correctly. Okay, everyone. Otherwise, if there aren't any more questions, I think we're good here. Very much good luck on your quiz tomorrow. Make sure that you ask Ali for things. I'm actually not around tomorrow. So for your quiz 2, I will be the person to go to. But for quiz 1, make sure if you have any questions, you ask Ali. And then otherwise, I don't think I'll see any of you until after reading week, right? Next week is reading week. So good luck on your quiz and have a great reading week. And I will see you on the other side. Okay. All right. Thank you, everyone. Thank you. You too, Justin.